Hi, and welcome to a calculus video where we're going to look at more power, product, and quotient rule derivatives. So one derivative that you may have been exposed to before is the derivative with respect to x of e to the x is itself e to the x. Now, while I can't necessarily give you a formal proof yet until you get to natural log differentiation and some implicit differentiation, I'd at least like to show you the graph so you can see it from a slope of a tangent line perspective. Okay, so if I graph the function f of x equals e to the x, and then I take a look at it, we should recognize what that exponential growth function looks like. Crosses the y-axis at 0, 1. Certainly, as x approaches negative infinity, is leveling off or getting close to 0. And as x is increasing, this is getting larger and larger very quickly. It's exponential growth, right? So here I'll kind of zoom in. So here's my function, f of x equals e to the x. All right, this function is always increasing. If you look at this function from left to right, read it just like you would a book, you would say it's increasing, which means its derivative should always be above the x-axis, okay? Because its slopes of its tangent lines are all positive. Further, the slopes of the tangent lines close to that -8 are very, very flat or close to 0. But as x increases, these slopes are getting larger and larger. So if you drew a tangent line, let's say at x equals 0, you're going to see that that slope is actually 1. Well, okay, it crosses through 0, 1. And as x increases, the slopes of the tangent lines get larger and larger and larger. So if you actually graphed, hey, what's the slope of the tangent line at each point, you're going to see again that as x goes to negative infinity, it's flat. So first of all, it's always above the x-axis, right? Because our function was increasing. So our derivative graph should be above the x-axis. It's flat for negative x values as x approaches negative infinity, so closer to 0. And then the slopes of those tangent lines increased as x increased. So that's why you're going to see from a graphical perspective that the slopes of the tangent lines of the graph of e to the x end up looking like e to the x. So that's what you're getting there. Okay, the other exponential function that we're going to study is any constant to an exponent that is a variable. So something like a to the x, 2 to the x, 5 to the x. That derivative is itself similarly to e to the x, but then you have to say times natural log of a. Because technically, if we have a function e to the x, its derivative is actually e to the x times natural log of e. But see, I don't need to really write natural log of e because natural log of e is 1, but that's why if you have something like, for example, 2 to the x, then my derivative is 2 to the x, it's itself, times natural log of 2. And again, once you get natural log and implicit differentiation under your belt, you can see the proof of this really nicely. Okay, now fundamentally, I want to make sure you understand one difference. So I'm going to go off to the side here real quick. You have seen so far functions like, this is a little darker, y equals x squared. That's a polynomial where my base is my variable and my constant is in my exponent. That needed power rule for the derivative. So I would have said y prime, bring down your exponent, because again, that's a constant. Keep your base the same, that's where your variable is, and subtract 1. We don't necessarily have to write to the first, but you certainly can. And that's just power rule differentiation. That's vastly different from what we're saying we have right here. I have something like 2 to the x, where my base is actually a constant and my variable is now in my exponent. So I cannot use power rule because if you thought, oh good, I'll power rule this, so when you're finding the derivative of this, you would bring down your exponent. Well, that's kind of odd because that's a variable, but okay, let's just keep going here. Keep your base the same, and see now when you subtract 1, you're getting x minus 1. You're not getting a value or a constant, some number. So that's how you know power rule was not on the table. You did not have where your base was your variable and your exponent was a constant, like some polynomial. You actually have something exponential. So I would have to say, if I have something like 3 to the x, that I need this constant to an exponent rule. So this is 3 to the x times natural log of 3. All right, so let's put this in practice with some product and quotients. So what I see when I look at this is I see that I have a product in the numerator. 5x is one function, e to the x is another. So I'll highlight those two different colors. 5 to the x is one function, e to the x is another. And then in my denominator, I have x plus 9. Now, you can't just take the derivative of the individual factors here. You are actually applying quotient rule. So this derivative would be low, so I'm going to copy down the low, d high. So now I need the derivative of this numerator. Well, that's product rule. Product rule says do the derivative of the factors one at a time, and I'm just going to do the derivatives in the order that I see them. So derivative of 5x is 5. I will leave e to the x alone, plus carry down your 5x. And now technically I'm doing the derivative of e to the x, although you can't tell because it's e to the x. So this was my low, and all of this is my derivative of the high, or the numerator. Minus your high, I'm going to copy it down. D low, now I'm doing derivative of that denominator. 1. That's kind of nice. Derivative of x plus 9 is 1. So minus high, d low, and this is all over low squared. Now, you are totally welcome. This is the correct derivative. You do not have to necessarily simplify it. I'm not sure that I would type it in this way if you're typing something into, a more type system. For example, I'm not going to type times 1, things like that, but you have found a correct derivative. If you wanted to sort of simplify this, you could. I'm going to leave this x plus 9 factor, 5e to the x plus 5x e to the x is going to stay. And I'll just write minus 5x e to the x, because again, I'm not going to write times 1. And then if you wanted, you can actually factor out of 5e to the x, because it factors out of here, and it also is going to factor out of here. And again, here's your first term, here's your second term. You have two terms in your numerator. So if you wanted to, you could factor out 5e to the x. So I have x plus 9 as a factor. 1 plus x is what's left in the parentheses, because if you factor out that 5e to the x, you get a factor of 1, and then just x in that second term, and then minus x here. And I certainly could keep going because this numerator does get a little bit nicer. You do not have to go this far unless you wanted to. So let's see, if I multiply or expand this out, binomial times binomial, so I get x times 1 is x times x is x squared, 9, and 9x, so I have 10x. So I have x squared plus 10x plus 9, oops, minus x, don't forget. And the minus x was right here, all over this x plus 9 quantity squared. So I could certainly have said then just plus 9x, right, instead of plus 10x minus x. That looks a little bit better, but certainly not necessary. Once you get into later derivatives, you will certainly need to simplify. Okay, let's do one more. So in this problem, again, you can look at it and see, can I simplify anything from the beginning? That answer is going to be no, because you have a binomial in your denominator, so you would not be able to separate and reduce or rewrite this fraction in any way at this time. So I'm going to leave it alone, and I'm going to use quotient rule. And so again, here's my high, here's my low, and I will apply quotient rule with the fact that I know when I need the derivative, so if I have a function 2 to the x, its derivative is 2 to the x times natural log of 2. And so if I needed the derivative of 5 to the x, its derivative is 5 to the x times natural log of 5. All right, so if I need those, I have them. So here we go. So this derivative, and I'm going to write this in maybe a notation that you haven't written a whole lot yet, but I want you to understand it for future use. You're taking the derivative of y with respect to x. So that's dy over dx, right? That reads the derivative of y with respect to x. Y is your output, x is your independent variable or input. So I'm going to apply quotient rule. So it's low, so I'm going to copy down the low. D high, now here's where I need that derivative of 2 to the x. So it's 2 to the x times natural log of 2. That's my low D high minus my high, and make sure you're keeping your parentheses here, D low, and the derivative of the low, I know the derivative of 5 to the x is 5 to the x times natural log of 5, and the derivative minus 7 is 0. So I have my low D high minus high D low all over low squared. I do see 2 to the x in each term if you wanted to maybe factor that out. Because again, you have two terms in your numerator when you do quotient rule. You have your low D high and minus your high D low. So if I see something that I can factor out, it might be both easier to type in and also easier to solve later on in the course. So I will do a quick rewrite here. This derivative is, I'll factor out a 2 to the x, and that's really all I can factor out actually from that numerator. So I have 5 to the x minus 7 and natural log of 2 in my first term left over, and just that 5 to the x natural log of 5 in my second term. And then it's all over 5 to the x minus 7 quantity squared. I also don't want you to get in bad habits because some people see these first two factors here of this 5x minus 7 and think, oh good, I can reduce that. They divide to 1, but they do not because that is a cross subtraction. So if I could have simplified that, I would have just simplified it in my quotient rule formula, and there would be no need to have both. But you're first multiplying the low times that D high. So I need to multiply all this before you're doing any division. This fraction bar acts as like parentheses or a grouping symbol. It's a separator. So the only way you can divide something out is if you factored it out, but that doesn't match my denominator, so nothing really divides or simplifies. So here I am. I hope you found this video helpful, just on maybe a little bit more of product, power, and quotient rules with some exponential functions built in. Thanks for watching.